This is problem number 4 on the practice problems for test number 3. Demonstrate whether each of the following series converges or diverges. For part D, state whether it converges absolutely, converges conditionally, or diverges. A, summation n equals 1 to infinity of e to the negative n. First thing we're going to do is write out the first few terms here, just because I don't quite know what this series is. So e to the negative 1 plus e to the negative 2 plus e to the negative 3 forever. And I'll go ahead and rewrite those so we don't have negative exponents. Just really want to see exactly what this series looks like. And if it's written that way, I'm really hoping that we can look at it and identify it as being a very special series. This is a series where there is a constant ratio between the terms. We keep multiplying by the same thing to get from one term to the next. In this case, the constant ratio is 1 over e. And if there is a constant ratio, then it's geometric. With the common ratio equal to 1 over e in this case. And we know that the common ratio here is less than 1. That's the cutoff between the geometric series which converge and the geometric series which diverge. So in this case, the common ratio in absolute value is less than 1. This series converges. That's all that we have to do for this problem, but because it's geometric and it converges, we may as well just actually continue on and write down what it converges to. So it converges to, the formula is a over 1 minus x, where a is the first term, 1 minus, and the common ratio is 1 over e. And we can clean this up just a little bit. So this is really 1 over e divided by 1 minus 1 over e. How about we multiply top and bottom by e? So if we multiply the top, this guy by e, then we just get 1. And if we multiply this whole thing times e, the e will distribute. And let's see what we get. So we said upstairs multiplied by e, we just get 1. Downstairs, the e distributes, and we get that. So that 1 over e minus 1 is exactly what we get if we added up the terms of this thing forever. Part B, summation 5 plus n over n squared. Okay, again, I'll write out the first few terms just to see if I can get a handle on the series. So plugging in n equals 1, 6 over 1 squared, plus plugging in n equals 2, 7 over 2 squared, plus n equals 3, 8 over 3 squared. We'll do one more, 9 over 4 squared. Okay, so my first impression is this is definitely not a geometric series like the previous one. There's certainly no common ratio going from one term to the next. I do very first just see if the terms themselves are approaching 0. In this case, hopefully we can see that they are, right? Because the n squared part is going to get bigger much faster than the 5 over n part. So indeed the terms go to 0, which is unfortunate because otherwise that would have been the end of the ball game by the nth term test for divergence. All right, so let's see if we can figure out what we feel this thing is doing. So the 5 plus doesn't seem to make much difference. So basically the series is similar, and I'm going to use the word similar because, I mean, we'll have to write it up more formally when all is said and done, but let's just kind of work through the thought process here. So series is similar to the summation of just n over n squared, ignoring the 5 there. And that's, by canceling, that's the same as the series 1 over n. And that series is famous. It has a name. I'd like you to know the name of that series. This guy is called the Harmonic Series. And I'd also like you to know whether it converges or diverges. It is just a straight fact. We saw it in class. The Harmonic Series diverges. So that is the divergent harmonic series. So I can't imagine the 5 plus is going to make much difference, which leads me to believe the original series that we're given here is also going to diverge, but we have to write it up more formally than we have here. So we have a couple of choices here. You might first just try a straight comparison test. I have a series that diverges. The hope is that this thing right here, let's see, do we want it to be smaller or bigger than something divergent? Bigger is the only useful direction. So the question is this guy bigger than this guy? And the answer is yeah. I mean, you're adding 5 to the top, so it's definitely bigger. So I think we can just use the comparison test or the direct comparison test here. Since 5 plus n over n squared is definitely bigger than n over n squared, and since the sum of n over n squared diverges, that's the harmonic we just talked about, comma, the sum of 5 plus n over n squared also diverges. By the comparison test. Okay, so this one is done. We've got everything we needed. We also got a little bit lucky here. If instead of being 5 plus n, it had been negative 5 plus n, well, still, I don't feel the negative 5 will make one bit of difference, but negative 5 here means that this inequality is not the right direction. The inequality would flip over, and it would be useless to us. So in that case, you would want to use the limit comparison test. So let's go ahead and write that up just so that we make sure we have practice doing the limit comparison test, just in case we don't get lucky like we did in this case. Okay, so put a line there. The proof is done. But if it didn't happen to go as well as it did just there, we'll try the limit comparison test. Okay, remember the limit comparison test, we're going to take the term in our series, 5 plus n over n squared, and we're going to divide that by the term in the series that we know something about that's comparable. The comparable series here was 1 over n. So 1 over n is the thing that we're going to put right there. Okay, and what we want to do is find the limit of this thing as n goes to infinity. I think this guy's supposed to have absolute value around it. If I'm wrong, then I'm wrong. But in this case, everything's positive, so it doesn't matter. So this is the limit as n goes to infinity of, so upstairs we get a 5 plus n over n squared. I'm going to flip over, instead of dividing by 1 over n, I'll multiply by n over 1. I'll lose the absolute value because everything is positive already, so it doesn't matter. Limit n goes to infinity. One of the n's cancel here, so that goes away, and this becomes just n downstairs. So we get 5 plus n over n. And that limit we know because we know that when you have a polynomial upstairs and downstairs, and you're sending the variable to infinity, all that you look at is the leading powers, right? So the 5 doesn't matter here. We just look at n over n, and we get 1. So this limit is 1. And that's a good thing. So then maybe we'll give a name to this so we don't have to rewrite it. I'll just call it L for that whole limit. Since L is not 0 and not infinity, in this case we got 1, all we need to do is make sure we don't get 0 or infinity for the limit comparison test. So since that's true, then the sum of 1 over n and the sum of 5 plus n over n squared behave the same. By the limit comparison test. Either they both converge or they both diverge. And in this case, we've already established that the sum of 1 over n is the divergent harmonic series. Then we have that the series in question also diverges. Okay, moving on to 4C. summation n factorial cubed over 4n factorial. So in this case, I see factorials. I mean, you can write out a few terms if you wish. I think that's never a bad idea. But as soon as I see factorials, I know I'm going to be using the ratio test. And this problem is going to stretch us a little bit in terms of our comfort with factorials, but let's push through. So ratio test involves taking a limit as n goes to infinity of a sub n plus 1 over a sub n. Again, absolute value. I'll just give it a name. I'll call it L. And let's go ahead and start doing this calculation. The biggest part of this problem, aside from recognizing we should use the ratio test, is doing this calculation. So a sub n plus 1, well, let's start downstairs. That's easier. It's just a sub n, which is the original term in the series. N factorial cubed over 4n factorial. Upstairs is the next term, the n plus first term. So all of the n's that we just wrote downstairs get replaced with n plus 1s. So this becomes n plus 1 factorial, and it is cubed, divided by 4 n plus 1 factorial. All the n's become n plus 1s. Okay, so let's clean this up some. So I'll write the n plus 1. I'm going to run out of space, so let's go down here. So this equals limit n approaches infinity of. So upstairs we have n plus 1 factorial, and it is cubed, divided by, I'm going to go ahead and distribute that 4n plus 4 factorial. And then we're going to change the division to multiplication and flip over the whole thing in the bottom. So we now have a 4n factorial here and an n factorial cubed down here. And I'm going to stop writing absolute value because, again, all these things are positive. So absolute value is irrelevant in this one. All right, so here's where we got to really know our factorials to be able to do some canceling, because this is a mess. Certainly, I don't want to distribute everything out upstairs and downstairs. So let's see if we can start writing out some of these factorials and cancel some stuff. So let's look at first two terms I want to look at, or I'll highlight here in yellow, those two terms. So suppose that I just had a single, forget about the cubed, but suppose that we had an n plus 1 factorial divided by n factorial. Now these two things cancel. They cancel quite significantly. But without practice with factorials, it's really not clear that they cancel. So if you have something like this and you think, well, how do they cancel and do they cancel? I'd encourage you to just plug in a number. Like if you plug in n equals 7. So if n is equal to 7, then upstairs I have 8 factorial and downstairs I have 7 factorial. And once we got some numbers, then maybe we can be a little more comfortable. 8 factorial is 8, 7, 6 down to 1, and then 7 factorial is 7, 6 down to 1. And so everything cancels except for the 8. And so can we bring that back to this guy, n plus 1 factorial over n? Everything cancels except for a single n. A single n plus 1. So n plus 1 factorial divide n factorial is just n plus 1. It's like the 8 that was upstairs. So what we have highlighted here in yellow is going to cancel quite significantly. So we're going to cancel and we're going to get n plus 1. But we actually have 3 of those terms in yellow because it's all cubed. So I think we're going to end up with n plus 1, n plus 1, n plus 1, n plus 1 cubed when all is said and done. So let's write that. Limit n goes to infinity. N plus 1 cubed is what we have left when we cancel all the stuff in yellow. Now, the same kind of thing happens with the 4n factorial and the 4n plus 4. But until you practice with it, it's not clear what's going to happen. So let's look, I'll highlight here in green the other terms. So 4n factorial, 4n plus 4 factorial. And so I'm just going to write that here in green. And there are lots of ways to think you are correctly canceling and to do it wrong. So I'd encourage you to just pick a value for n. For example, if we said n is equal to 2, And then upstairs, 4 times 2 is 8. So upstairs is an 8 factorial. Downstairs, n is still 2. So 4 times 2 is 8, plus 4 is 12. 12 factorial. So if you cancel this, you write out a few terms if you want to, but the 8 factorial will cancel completely. And what will be left from the 12 factorial? Well, we'll have 12, 11, 10, 9. And then the rest of it, 8, 7, 6, etc., is going to cancel entirely with the 8 factorial. So we would get 1 divided by 12, 11, 10, 9. So why did that happen? Well, downstairs we had a 12 factorial. The 12 is the very first thing that appears here, and then you get 4 terms. How come 4 terms? Because this guy here on the bottom is exactly 4 more than this guy in the parentheses here. So that 12 and that 8, the difference of 4, is why you have these 4 terms sitting out here. So I think that we can then say that the green things are going to cancel. The 4n factorial upstairs is going to go away completely. This thing will remain in its current form. It'll be a 4n plus 4. That's like the 12. And then we've got to write the 11, 10, and the 9. So 4n plus 4 is the first thing, so we'll write that here. And then times, all right, so what's the 11? 11 is 1 less than 12. What's 1 less than 4n plus 4? It's 4n plus 3. And then 1 less than that. And then 1 less than that. And it ends right there because the very next term would be 1 less, which would be 4n plus nothing. But that 4n would cancel with this 4n, and then the next term would cancel with the next term from this factorial up here, and everything would cancel from there on. So I think we've got it. So it's this. Okay, so the question now is, what is this equal to in the limit? Okay, so our job now is to figure out what the limit of this big blue thing is. So ultimately, I'm interested in what the power is upstairs. So if I were to distribute this n plus 1 cubed, then ultimately I would get this. So this guy is equal to limit as n goes to infinity. So I don't want to distribute it all the way out, but I definitely know it'd be n cubed plus some n squareds plus some n's plus a constant term. So upstairs is that. And downstairs, I really don't want to distribute this thing through. But what will I get if I multiply the thing with the n in each of these terms? So it's 4n times 4n times 4n times 4n. So that is 256 n to the 4th plus, and then you'd have some n cubes and n squareds and n's and then constant terms. I don't care about any of those. Because since n is going to infinity in this limit, all I need is the end behavior. And that's dictated entirely by the leading terms. So what happens here? Well, there's more n's on the bottom. So what will this limit, what is this limit equal to when n gets really big? Well, more n's on the bottom and it goes to 0. Okay, and is 0 a good number or is that the inconclusive number? All right, so remind yourself of the conditions of the ratio test, which is what we're using here. And 0 is a very good number. Any number less than 1 would be a good number right there. And 0 certainly fits the bill. So let's refer to this big limit. I called it L from the very beginning. So let's write down here our conclusion. Since L in this case was equal to 0 and it was less than 1, by the ratio test, the series in question, let's copy it from up above. What does it do? If we're less than 1, then the series converges. Okay, we've got one more part here, part D. Summation -1 to the n over square root of n. And we need to state not just whether it converges or diverges, but if it converges, does it converge absolutely or conditionally? So the reason that comes into play here is because if you write out for the first 2 terms, you'll see that this is a series that's a little bit different than any of the ones that we've seen before. So when n is 1, I get -1 over square root of 1. I'll just write that. Plus, now n is 2. It becomes +1 up there, square root of 2. When n is 3, it's back to a -1. And so we see here that this is what kind of a series? It is an alternating series. And if it's an alternating series, then we might try the alternating series test. But before we try the alternating series test, let's just go ahead and be greedy. If the series converges absolutely, that is to say, if it converged even if it were all positive, then automatically it converges. If it converges when you get rid of all these negatives, then it certainly converges in its current form. Because in the current form, we've got some cancellation, whereas if we make them all positive, then the series just gets bigger and maybe it blows up to infinity. So let's be greedy and just see if we can figure out, does the series converge if it's all positive? Because if the answer is yes, if this series converges, then automatically the series in question, the series above, converges as well. Okay, so we start with this, which is the same as the absolute value of the original. Okay, so let's see, that one right there is equal to the sum of 1 over n to the half. And I'm hoping that you know the name of that series. This is a special series. We've given it a name. It is called a p-series. And in this case, the p is equal to a half. It's your job to know whether that's convergent or divergent. The magic cutoff for p-series is 1. So it's a p-series which diverges since p equals a half, which is less than 1. So it definitely does not converge absolutely, because when I took the absolute value of the original series, turns out the thing diverges. So that's too bad, because if the answer had been it converges, then we'd be done with this problem. Okay, so it definitely doesn't converge absolutely. So the next question is, does it converge conditionally? Meaning, all right, so we can't deal with it all being pluses, because if it's all pluses, then the series diverges. That's what we just found. So maybe it converges with those negatives. Maybe there's enough cancellation happening. So this is where we use the alternating series test. So the alternating series test involves 3 things. So first thing we're going to do is ignore the negative up there. Said another way, we're going to take the absolute value, and we'll get down to exactly the thing that we just considered. So there are 3 parts to the alternating series test. First thing we need is for the terms to all be positive. And well, of course they are, because we just ignored all the minus signs, so that's good. Check. Next thing we need is for the list of terms to be decreasing. Said another way, you need an plus 1 to be less than a sub n. Well, let's see, as n gets bigger, what happens to that 1 over square root of n? Well, it gets smaller. It's going to go to 0. So, so what do we have here? So then we can say that 1 over the square root of n plus 1 compared to 1 over square root of n. That's just looking at the n plus 1 term and the n term. Well, definitely the first one is smaller, right? Because the denominator is bigger. So that is another check. And then finally, we need the limit of these terms, ignoring that minus sign, to be 0. That's the magic number. Okay, so let's see if we can verify this. Limit as n goes to infinity of 1 over square root of n. What's it equal to? Well, if n is really big, then the fraction is 0. It's kind of anticlimactic, actually. I mean, if you know that you're supposed to use the alternating series test, and you know the 3 conditions, then checking them can oftentimes just be rudimentary. You just go through and it's a hoop and it's done. And like I said, it feels anticlimactic. But I think we've got our 3 things. So because of those 3 conditions, then we can say by the alternating series test, the series, square root of n down here, 1 upstairs. So that one isn't the one the alternating series test applies to. The alternating series test applies to the original one with the negatives. By the alternating series test, this series converges. And so that's a big part of this problem. And then our our last piece here is we have to decide, does it converge conditionally or does it converge absolutely? So since the sum of this guy converges, but if we took a look at that same guy in absolute value, then it just becomes a 1 over square root of n, which we've already seen diverges. Then our conclusion is that the original series in all its glory with those negatives, how does it converge? Does it converge conditionally or absolutely? This is the very definition of converging conditionally.